Lesson 27 is going to be about entropy. So we're going to talk more about entropy, which we said last time in lesson 26 we would call that disorder. We learned about the first law of thermodynamics last time, and now we're going to learn about the second one. And if you remember, we said there was 3, so it means we have one more to learn about after the second one. All right, so we have to bring back some important definitions. So the first thing says measuring entropy. Entropy, and this should be, see, this is, I'm not sure why that says 16. Maybe because of chapter 16, but it should be 27a, okay, just in case I put these into separate, smaller videos. So entropy is a state function, and what does that tell us? Now we have to think back to what state function and non-state functions were. And so in this case, if entropy is a state function, it means that entropy only depends on the initial and final states, not the path we take to get there. Meaning it doesn't matter how many steps it takes, all that matters is point A to point B, not all the stops in between. Okay, so entropy is a state function, and then just to review what state function is, there's a brief reminder. We talked about if you have a mountain and how the elevation was a state function, but the path to get to the top, if our person's up there on top, the path to get there was a non-state function. Okay, so the amount of maybe steps taken, pedometer-wise, things like that. Entropy values can be measured using calorimetric methods. The values given in the tables are typically in standard entropy values with the S naught, and so it's like N-A-U-G-H-T. Naught is what the little degree symbol means here. And so what this tells us is when we have that naught symbol, it means we're looking at the standard molar, so when N equals 1 mole, state, and this is so that values can be compared. Because if you remember back to when we talked about heat and how one match is only going to produce a little bit of heat, but if we have an entire bonfire, that produces a lot of heat. So in this case, if I have 1 mole of something that's slightly entropic versus 10 moles of something that's slightly entropic, if I have different amounts because of it being a state function, then it's going to have different entropy values just because I have different amounts of it. So we're going to hold everything to 1 mole. And so these are an example of our entropy values here. You can see it. There are a couple of important things. We have standard molar state, joules per Kelvin times mole. So all temperatures must be in Kelvin if it's this particular unit. And then if you look over here, we have liquids, gas, and solids. And the entropy values are going to differ based on the physical state. And if you think back to chapter 26 at the very end, lesson 26, we said that the phase of the compound had an impact on the entropy of the system. Okay, so it shouldn't be a surprise. So let's look at some trends that we see. I should also say up here that this is at STP. So y'all remember STP is temperature is 25 degrees Celsius, 298 Kelvin, and pressure is 1 atm. Okay, so at STP. So list some trends that we can see. Well, we can see, 3. So I'm going to write them right up here. Okay, the one is that as you go from solid to liquid to gas of the same compound, the entropy is going to increase. Okay, so entropy increases. So from liquid to gas, it goes from, for water, from 70 to about 189. If we go look at solid to gas of iodine, it goes from 116 to 260. So that's one. The second is that as our molecular weight increases, so it becomes heavier, the entropy is also going to increase. So comparing neon and helium, helium is much lighter than neon, and its entropy value is also smaller than neon. The third one is that as we have a more ordered structure, the entropy is going to go down. So to compare that, let's look at carbon when it's diamond and graphite. We remember that diamonds are very ordered, long-range crystalline structures. Graphite, we said, was less ordered, less structured, and its entropy value is higher because it's less ordered than diamonds. Okay, so those are three trends that we see based on just those little bitty values that were given in 17.1. Now, in your textbook at the very end, there are tons of entropy values. They are not things you need to memorize, so you will always be given them. The only thing you're really accountable for is making sure you're looking at, one, the right substance, two, the right phase, because that has a big difference on the final numbers, and then always just make sure that you know what your units are. You know, Dr. Smith is, you know, I'm a stickler with units. I want them on every single answer, and also the zero from the decimal place. And so I'll give you an example of why units are important. So yesterday was Thursday, and my son was learning about addition, and he's watching a little YouTube video about addition with a pirate. And then I was supposed to ask him this question that the teacher told me to ask, and it was if, I think it said, you know, John saw 6 lions and Sally saw 4 monkeys. How many lions did they see? And he told me 10, because in the video, it was, the only thing they show them in the video is, you know, if you have 4 of this and then 2 of this, that equals 6. And so he knows how to write 4 plus 2 equals 6. But what the video doesn't teach him is what they're talking about. He knows how to do the how much. He knows how to write the how much down, but he hasn't learned the of what yet. How much of what and its importance. And so I kept asking him, like, listen to what I'm saying. 6 lions, 4 monkeys. How many lions? And that's where units become important. And it's a great illustration to me of why I need you guys to always tell me units, because I don't know if you're adding lions, monkeys, bears, or apples. And so just a brief side note, also a glimpse into what teaching kindergarten looks like for me right now. All right, so second law of thermodynamics. Okay, this is the second part of this particular lesson, and so this should actually be 27b. The second law's definition says the entropy of the universe increases in a spontaneous process, meaning no energy required, and remains unchanged in an equilibrium process. Okay, so that means when K equals Q at equilibrium, entropy should be equal to 0. Okay? So, may kind of see where this is going, that K and Q are going to come back, and they will. So let's define the following processes as they relate to thermodynamics. Remember, we did a little bit of this when we did calorimetry. The universe is the sum of the system plus the surroundings, so it's everything, okay? All things. The system is usually going to be the reaction, which is what we are studying, measuring. And the surroundings is going to be the area around the reaction. And it's the part of the universe that's interacting with the system. And And it's much harder to study the surroundings because it's everything else. But if we can study and understand our systems, we can apply the surroundings, or we can apply that knowledge to the surroundings and have a better understanding. So this law can be summarized mathematically, that the entropy of the universe, which is the sum of the system and the surroundings, is literally always going to be greater than zero. Spontaneous. So entropy is increasing, okay? Now, as far as like astrophysicists are concerned, this is also something that they see, that the universe is constantly expanding, which is part of the entropy process. It also is what we see in aging. When you're born, you're developing, the cells are growing in utero, you're born, and then at some point you grow, and then growing stops, and then you start to reverse the process, and you start to, things start to stop working, things start to age, and that's an irreversible process. You cannot stop growth, but you also can't stop the aging process. No matter how much Botox or plastic surgery you have, you're not reversing aging. You're just simply kind of patching the hole, if you will. Same thing with houses. Once we build a house, you know that if buildings go without maintenance over time, they are going to become dilapidated buildings, and that is also entropy. Okay. Now, when we have the entropy of the universe is will equal zero when we're at equilibrium. So we know this is where K and Q are equal to each other. So let's calculate the entropy change of the system. Okay, so just looking at the entropy of the reaction, which is also going to be the entropy of our system. Okay, so what we're studying, because that's what we defined above. Now, the delta entropy of the reaction is going to be equal to the sum of all the entropy values of the products times their stoichiometric factor minus the sum of all of the entropy values for the reactants times their coefficient. And then you just take the difference between the two and you report the final value. Report the final value in units of joules per Kelvin. So first, let's predict the sign of entropy change for the following equations. So looking at left to right, I see that I'm going two different gaseous substance to something that's gas. I have 2 on one side plus the third, so 3 going to 2. So anytime I have a decrease in the amount of moles, so I'm going from 3 to 2, this is going to suggest a decrease in entropy, meaning delta S will be less than 0. When I go from 3 O2 molecules to 2 ozone molecules, I'm making the same kind of change. So we're going to see that the entropy is less than 0 because it is decreasing in entropy. On the third one, I'm going from a solid, which is something that has less entropy, to something that is solid, liquid, and gas, where liquids and gases are more entropic. I'm also going from 2 to 3 things, so I'm adding up the coefficients. So I'm going from 2 to 3, but I'm also going from a single solid to solid, liquid, and gases, which are all more entropic than the solid in itself. So my entropy is going to be greater than 0. Let me keep this consistent. Increase in entropy. Okay. The last one is going from 2 gas molecules to 2 liquid molecules. So there's no difference in moles left on moles on right. However, I am going from gas to liquid, which is the gases are more entropic than liquids. So this would suggest a decrease in entropy where delta S would be less than 0. Okay? All right. So let's practice calculating some actual numbers, not just predicting the sign, but calculating the values. I'm going to do 2 of them and leave y'all to do 2 of them to see if you get the same answer. This is what we would normally do in class, and then we'll talk about entropy of the surroundings. All right, so using the table below, which is down here, so I'm going to keep my table down there and I have my paper in front of me. We are going to calculate the entropy for A. And so what I normally will do, just to keep myself nice and organized, is I write the values from the table right above them. And this way, if I make a mistake, like say I do the calculations, it's multiple choice, I look on the multiple choice and my answer's not there, well, the first thing I'm going to check is, did I actually pull the right numbers, including the phases, and make sure that I haven't made the mistake there. Now, the reaction is going to be products minus reactants. So I'm going to start with my magnesium chloride. And I'm going to use brackets. I have 1 mole of magnesium chloride times its value 89.5 joules per Kelvin times mole. And I only have 1 product. I'm going to subtract from that the 1 mole of magnesium times the 32.5 joules per Kelvin times mole. I'm going to add to that the 1 mole of the calcium or the chlorine gas times its 223 joules per Kelvin times mole. And now I'm going to take care of the stuff in the brackets first. My moles will cancel out because I'm multiplying them. And that's going to leave me with 89.5 joules per Kelvin minus, when I add the 32.5 and the 223, I'm going to get 255.5 joules per Kelvin. And this is going to give me a negative 166 joules per Kelvin. Oh, shoot. I just meant to highlight that. There we go. Okay? All right. So I'm actually going to leave y'all with a 3 to practice. Never hurts to practice this. Okay? I would even practice making my predictions first. Like the A, I went from a solid and a gas to a solid. I went from 2 to 1. So I would have predicted that this would have been well, that's not right. A decrease in entropy, and that prediction would have been right. Okay, they both check out. All right, so y'all practice the other 3 by yourselves. All right, entropy of the surroundings. We're going to do the first one, and I'm going to let y'all do the last 3 because in order to finish this particular part, you do need the entropy the value from the previous equation. Okay, or you'll have to calculate something about the previous equations. So it says for the constant pressure process, meaning so pressure is going to stay the same. So let's write delta P, change in pressure, is 0. The entropy of the surroundings is proportional. Is proportional to the enthalpy of the system through the following equation. Okay? So you need to know this equation. So it says, using the table above, calculate the entropy change of the surroundings for the following reactions. So remember, we can't necessarily calculate something about our surroundings, but if we know enough about our system, we can understand our surroundings. And in this case, we have to know what the enthalpy of our system is, because that's all we can determine, or all we can directly measure. So now we're going to go up, and we're going to look in the second column, the column we didn't use. So we used that one for this, and we're going to use this equation, or this column, for down here. Okay, so I can see, I'm going to write in my numbers above. Magnesium solid is 0. Calcium gas is 0. and magnesium chloride is negative 641.8, and the units are going to be in units of kilojoules per mole. So no kelvins. Okay. So I'm still going to do products minus reactants. So I'm going to have 1 mole of magnesium chloride times the negative 641.8 kilojoule per mole in the bracket, minus the 1 mole of magnesium solid times 0 kilojoules per mole. So I usually write these out just to make sure that I'm subtracting the reactants and products correctly, and also just in case I make a mistake. And I'm going to do the same thing for chlorine. So the moles will cancel out all the way across, and additionally this entire subtraction part will go to 0. And so what that leaves me with is the enthalpy of the system is negative 641.8 kilojoules. And if I want to convert that into entropy of the surroundings, I'm going to have to plug in into this equation divided by T. And I have to know what T is. So if I go back up, it tells me that it doesn't give us a specific temperature, but we do know that this means a temperature of 25 degrees Celsius, which was 298 Kelvin, that not symbol. So now I'm going to plug in my negative 641 kilojoule, divide that by my 298 Kelvin. This is going to give me a value, right? The negatives will cancel out, leave me with a positive. And this leaves me with 2.153 kilojoule per Kelvin. And if I wanted to convert that to be in the same units as the enthalpy of the systems above, I would change that to joules, which would give me 2,153 joules per Kelvin. Okay, and we're going to see why that's important on the next lecture, because we're going to start adding our values together. Okay, adding our enthalpy of the surroundings with our entropy of the surroundings with our entropy of the system to solve for entropy of the universe. Okay, so you have 3 problems to practice there, 3 problems to practice on 27C, and so then I will post the answers later on the announcement, like the weekly to-do list, so that you won't be tempted to use them unless you have to. Okay? All right. That's it for lesson 27. Make sure you finish the problems before you turn your notes into me tomorrow, or whatever day they're due on Thursday, but make sure you finish those problems or you won't get full credit for finishing your notes, okay?